All right, so good afternoon. This is the second talk of this year. We finally have a bunch of them scheduled, so we'll start returning to a regular schedule starting now and for the rest of this month and a little bit into March. And the first talk that we're going to be having today is from a good friend, Hyojoon Kim at Princeton University. And he's been my go-to for a lot of SDN-related topics over the past couple of years. And every time that we talk, he always tells me something new. So I was excited to hear about this one because I didn't know anything about this topic. So Hyojoon is going to be talking a little bit about their experiences with P4 on the Princeton campus and hopefully tell us all some great stuff. So I will turn it over to you, Hyojoon.
Thank you. Thank you, Jason, for the kind introduction and also giving me the opportunity to present our work in the CIE Brown Bag. So hello, everyone. My name is Hyojoon Kim. I'm going to present our work called Princeton P4 Campus, Building and Running Novel Campus Network Applications on the campus. And that's our webpage address. And I'm going to thank everyone who helped me do this work and also prepare the slides, Danny Chen, Jack Brassel, and Jennifer Beckford. All right, so I'm going to start with the gap that probably everyone knows. There's a research land and then there's production network, and there's a big gap here. So in the research land, researchers can come up with a new idea. The problem is that, but they're mostly are just tested on small and unrealistic experiments, and they actually never get a chance to go to the production network. They get tossed down. While the operator or practitioners on the production networks are using sometimes outdated tools and practices to fix the network, and they're busy doing that work. So we don't have a chance to see the new ideas actually applied. There's also a problem here where the new ideas are actually bad, but because they were never actually tested on the production network, it remains bad. Right, and someone can publish a paper, but it's the bad paper. So that's also a problem. That's the outcome of having this gap. So what we're missing here is a positive feedback loop, where I think we have a great opportunity where research and production network can actually help each other, but we're missing that because of this gap. So let me go into the network research pipeline we have in mind. I guess generally it applies to everyone in research, more or less. So it starts with the idea and design, and then we do a software implementation with some simulations or emulations. You use network simulators or Mininet for OpenFlow stuff or other OpenFlow stuff. For P4, it's called Behavioral Model version 2. It's a software emulation of things. And then you'll do a controlled lab experiments with synthetic traffic. Let's say you actually have a hardware and you can replace some synthetic traffic. The next step is to do a realistic lab experiments with real traces, if you can get hands on real traces. I see a comment. Is there a chat? Is there a question? Okay, sorry. The thing is that then you go to real deployment with live production traffic, and then the important thing here is that there's feedback loops from every stage so that you can actually refine your idea if it's bad and make it better. The problem here is that a lot of stages are missed and it's not possible. Starting from the third stage, actually, because we sometimes also miss the hardware to actually run these controlled lab experiments. It actually just stays in software emulation. So I'm quoting Jen here. It's hard to eat your dog food, so you keep drinking your own Kool-Aid. So this is a problem. So P4 Campus is an initiative to help create, deploy, and actually run experimental but useful network applications on a production campus network. And we primarily use programmable data planes and P4, so that's why we call it P4 Campus. So we're going to share some experience on this for the folks out there, so we can learn together how to do this. So first, a bit on programmable data plane. I don't want to go into so much detail, but So you first have fixed function switches, which use built-in commands, right? Then the OpenFlow came along and at some point, which allows you to program how to match, modify, and forward packets, where SDN kind of paradigm started. And then there's programmable switch, which is a programmable data plane, where you can actually program how to parse, extract bits, run some computations, although limited, and store some bits, match or modify, and forward packets. So in a nutshell, you can do much more functions in a switch now with a programmable switch. And this is not just magic or dream. There are actually commercially available programmable data planes out there. So just to cite a few of them is Netronome. There's this Barefoot Networks, Xilinx, and NetFPGA. And people probably all know NetFPGA. It's been there for a while. So you can do a lot of stuff with them. And there's this whole P4 ecosystem in the first place, actually. So there's a p4.org. P4 is actually the language you use to express your intent or like program, so that they can run in these programmable data planes. It's a language. So there's a bunch of different compilers. There's P4C, which is open source reference compiler for software emulation. Barefoot has their own compiler that will transform your P4 program and make it run on an edge-core wedge switch. That's just example switch, which has the Barefoot Tofino chip in it. There's a P4 to a NetFPGA compiler, which makes it run on NetFPGA Sumi. There's Netronome and Xilinx. So there's a whole ecosystem here, which makes everything actually possible. That's the point of this slide, basically. So that kind of actually clears the third stage here, because now you actually have the hardware where you can run your crazy idea and do some funky stuff in the hardware, and you can replace some synthetic traffic or download some PCAPs on public and actually play them. But these last two stages are still kind of hard to get to. And without these last two stages, new ideas barely actually see the light outside of the lab and the researcher's mind. So that's still a problem. So you're still missing these feedbacks from these last two stages. So why is it hard? Some are quite obvious, but of course, running on experimental stuff in production network is disruptive. I mean, it's all about uptime on operational networks. You don't want to put something really risky or experimental in a production network. Second one is user privacy. PII, or personal identifying information, is in production traffic. So operators will not and should not give just raw traffic PCAPs to researchers, and that's not allowable. There's generally also a lack of collaboration and communication between these two parties, I think. Generally because network operators are too busy putting out fires and doing all the work for us. So, and it's a different community, and we kind of lack that collaboration and communication. So you can think of an alternative, and it's a good alternative actually. You can have dedicated test beds, and that's what people did actually. Some examples are Planet Lab. There's Genie. More recently, Fabric. We had a really good talk on Fabric on CN Bradback ourselves. These are really good. I mean, they're real networks and they're WAN scale. I mean, they use real hardware is great. But we're seeing are some limited things about, they have limited access to actual production traffic, and not just like some actually, I think Fabric actually is hoping to have some like actual production traffic going on, but and some actually allow some production traffic, but there's kind of limited set of types and various types of production traffic you can get on these test beds, although a good alternative. So what I'm basically saying is production network is still a good, good testbed if you think about it. And there were some papers on OSDI also back in 2010, can a production network be a testbed, and so some ideas of how to do that, because it's kind of hard to give up that testbed. And so if you think about the campus, it's actually a very interesting place. It's hard to give up, because if you think of the campus network as lab, First of all, it's a very interesting place, right? Like all sorts of traffic is there. There's residential because there's dorms. You have science traffic from Science DMZ. Some campuses even have data centers, so you have data center traffic. And university and colleges and educational systems is running a business too. They have business traffic going on. And another interesting of a campus is it's open and dynamic, meaning like physically and electronically. It's open to the public. Like you go to the website, it should be open in general. And the campus itself is open. So you have many visitors and events happening. And because of that, there's so many BYOD devices popping up and going away and moving around. And the traffic actually you see on the campus is closest to the user, not just a tap on a backbone network in a larger scale. So, and also it's research friendly in general. So especially if it's a research focused university and do research, also teaching is important. But even if you go to the Princeton University website, it says enabling research, and enabling research is a core mission of a college and university. So they are generally research friendly. So this talk is basically about jumping the research chasm. Like actually jumping from research idea to real campus deployment so that we can actually get that feedback from these last two stages and jumping over these limitations of being disruptive and privacy concerns and lack of collaboration. So we'll try to share our experience here so that people can also learn from it or learn from it basically, yes. And also we can learn from you. So we have this cycle, which will guide me through the talk. So less disruptive means we have passive, you can focus on passive traffic monitoring as a gateway drug, we say. And then there's about preserving privacy, about campus data access, data anonymization, more collaboration, having a joint position. I'll go through this in more detail as we go through the talk. This is just the outline of the talk. And I will also at the end of the talk, I'll have demonstrate some successful deployments we actually had on our campus. One is OnTask, which is a line rate traffic anonymization system in P4. It's also an enabler of our work because it anonymizes traffic line rate for us. ConQuest is a fine-grained queue analysis. So every switch has a buffer queue in it, and using this application, we are able to detect microbursts and queue buffer fills or delays. SPINE-DNS is an active traffic measurement we actually did on campus. It's a DNS query anonymization because DNS query can be quite privacy sensitive stuff. So I'll also explain these applications at the end of the talk. So let's start with the being less disruptive. The general rule of thumb here, which kind of works in strategy, is to kind of focus on the passive traffic monitoring first. And this is just the kind of overall topology of a Princeton network. It has two ISPs. We have two Internet 2 connections, one in 100G, which is for the Science DMZ, one is 10G. And we also have a connection to YesNet. In more detail, we have two border routers, two firewalls, and one core and two data sensors connected like that. We are on the works of actually putting two cores. There's a lot of work making this happen. We actually had one core and one border in like just several months ago. But so this is the major uphill of our network. But the important thing is that we actually installed network taps in all these major links. So like, before it hits our border, after it hits our border, before the firewall, after the firewall, and all these important places, we actually installed network taps. And this is not just for our research, it was actually for the operational team. They had to tap everything so that they can monitor the network better. And I don't think this is just like really special to Princeton. I'm sure other universities have similar practices going on. The scale may be different. They may be bigger than us. They may be smaller than us, but some general practice is going on here. And this is already, many OIT and information technology offices actually have this infrastructure already in place. So, if you have a packet broker, that's better. which can actually guide you. So you can basically feed all the tabs to a packet broker, and our team actually feed that to a OIT traffic analysis tools. We have a bunch of them. I think we're trying to make just like reduce the number of tools, but that's basically what's happening on the operator side. What we basically said, like, can we actually borrow that packet broker? And if you have some time, can you also give us some mirrored live traffic to our data plane, programmable data plane testbed? And that actually worked because it's less disruptive. It's just actually mirrored traffic, and it doesn't actually go on the Precious network itself. So we actually were able to feed some really interesting live traffic, production traffic to our programmable data planes, and then we load the apps on our switches, and we can do some interesting analysis. And here our apps would like focus on doing some passive traffic monitoring analysis. The cool thing is we're actually looking at persistent traffic here. And tips on making this happening during traffic, taps are better than span ports. Probably people know this because span, you can do a span port too on a switch, but span generally burns a port. And also it uses a lot of resources on the switches if you have too many. If you have a packet broker, it really helps because it can help you remove or mask payload of the traffic so that researchers actually have no way of seeing the payload in the first place when you forward them to traffic. It can remove duplicate packets if you're typing from multiple places. You don't want to see packets. They also generally have some good filtering policies. So, for example, I want to only see DNS traffic, or like I only want to see mail traffic or something. Like you can actually do that. So that kind of helps making this simpler and easier. Okay, so that's about being less disruptive. Let's talk about preserving privacy because, okay, we can forward traffic, but is that okay? So then you have to do this thing about navigating campus data traffic access. There's two things here worth mentioning. There's institutional review board, which I think is every university or college might have. There's another thing about institutional review panel for use of administrative data in research. That's kind of specific to Princeton, but I'm thinking like other universities might have similar stuff. If so, let me know. It's basically about a review board of sharing administrative data on campus for research. So the IRB is more about rights and privacy and welfare of human subjects. The right one is more about feasibility. Can you make it work? What's the value of it to us? And what's the risk to the university? And is there any compliance issues when doing that? So you have to actually navigate this really well to make this actually happen. So it's a non-technical thing. You want to navigate well, I would say. So when you're preparing your IRB application, generally having these statements kind of worked. Basically, you want to say MAC and the institutes, for example, Princeton IP address will be anonymized before accessed. Payload will be removed before accessed. If not, the network operator will run the scripts and programs and provide the aggregate results, which doesn't include any PII to the researchers. So basically, you're showing that researchers have no way of accessing the raw data. So having these statements in the IRB application is critical. And you also want to say data will be stored and processed at the machine managed by IP staff. This shows that you will take good care of the data even if anonymized, because you don't want this data, even anonymized, to like moved to places and copied to places and put into public access. So you actually have to make sure you're going to take good care of the data if it's packet captures, basically. That's about IRB. About using administrative data, feasibility, you have to show how and where you're going to get this data. Is there any incurring cost of doing that? I think you just have to explain it well, that it's possible and there's no like crazy cost of doing it. The value, it was important to us. Like we have to show that the motivation and broader impact to the society. Is there any risk? We have to show that, oh, we will not see any sensitive private data that belongs to Princeton. If we do, we'll report it. And our stuff was also reviewed by lawyers on campus. So we were told to put these kind of notes, like note that we will disclose any collected data in response to a lawful request by law enforcement. So you may have these things, and it's generally good to follow those practices if they ask you to do so. So this is something to keep in mind when you're preparing an application or note for the use of unrealistic data, if you have some organization which checks this for you. All right. The third thing is the data anonymization. So this is more technical stuff. How do you actually do the data anonymization? So CIDA actually has a very good taxonomy of stuff and best practices and tools about data anonymization, because they actually share real data on their network, right? So these are some good links people can refer to learn about some tools and practices. Some tools we use on campus are CryptoPan, which is actually not a tool, a library about prefix preserving IP address anonymization. So it actually preserves the prefix if you specify it. So it's kind of good for having that subnet information still there. TCP MKPub is a good tool we found. It does prefix preserving IP address anonymization. It actually uses the CryptoPan library for this. It also does vendor preserving, MAC address anonymization. It updates the checksum if it changes anything. It can do field masking of ARP, IP, ICMP, TCP fields, and it truncates the payload automatically for you. So it's a very good tool if you're doing offline anonymization. So, and when you're sharing the data with researchers, I think these tools are good for you. There's other tools on the CIDA website where you can also find useful. But there's still a challenge if you think about, if people actually worked on anonymization stuff, there's still a challenge here. Because let's say you have a 100 gigabits per second connection coming up, and some researcher asks for, like, can I get a 1 hour packet capture anonymized? What the pipeline is, you capture it, and then on that captured PCAP file, you will run this tool. So you get an anonymous traffic and give it to the researcher. The problem here is even our campus, when we actually captured about 4 to 5 gigabits per second, 1 minute ended up to be about 45 gigabytes of storage. And think about what it will be for 1 hour. That's a lot of stuff. And then you have 2 copies because one is raw, one is anonymized. So you double that basically. And then there's a processing delay. This anonymization can take a long time. 1 minute actually on a good server actually takes 60 minutes to actually be done with processing all and anonymizing everything. So if that's 60-minute capture, that's gonna be much more. So it's still a problem. It's a lot of work for an operator. So the current workflow is slow and incurs a lot of compute and storage overheads. So that's why we kind of worked on this program called OnTest. It's a program, P4 program that actually runs on a real hardware where it anonymizes traffic live. So as the traffic comes in, it passes along and anonymizes in line rate. So it kind of simplifies the anonymization process and less work for the operators. And you know, as you do this, you don't even save the raw data. You all just get the anonymized version right away. So the good thing about that is you can capture it and send it to a researcher if you want, or you can just directly feed that to a researcher who has a switch, which can process that too. So some policies, example policy we can put in this program is you just use a option value formatted config file. So this is just an example. Like you can say like I want to anonymize the multicast broadcast or not. Keep the OUI of a source MAC, des MAC or not. You can also specify the subnets you want to do anonymize. It's prefix preserving anonymization. And you can say that yes or no. And then there's also that MAC and IP address in the ARP header. So you can say you want to anonymize that yes or no. So there's a lot of things you can do, a lot of different policies you can apply to this program. I will not go deep into this. There's always some work on it. We actually published a paper in the SITCOM NetAI workshop if you want to learn more. I think if you go to the ACM Digital Library, they even have a recorded talk given by Arpit. We also have a public source code, open source for the software behavioral model version, not the real hardware version, because we have some NDAs with that. So if people are interested in looking at this, they can go and check it out. So this is a good enabler of making data anonymization easier for us. So cool. So that kind of actually, this tool kind of enables us to clear the fourth and fifth stage here, because now it's kind of easier to give real traces to researchers because they're anonymized. And we have an opportunity to actually do live traffic, live protection traffic, meaning passively, not necessarily actively. So that was great. And then the third wheel is about more collaboration, and I will tackle this subject. So the strategy kind of works for us is having a joint position, which is kind of basically me in this case. So I'm a person who has access to both worlds. Jen find a good picture of a person having two hats here. So one is, on the one hand, I'm a research scholar in the Department of Computer Science, so I have access to new and bold ideas. I have access to new technology. I have regular meetings with faculty, scholars, and students who want to do some good research. I am also the cyber infrastructure engineer on the OIT side. So I have experience with real world problems and issues. I have access to current infrastructure, and I have meetings about the problems on campus or the future campus plan and strategy. So I'm in both worlds, and it's a good balance, basically. And I kind of act as a bridge over the research chasm, so I can bring new problems to researchers. I can I can also organize meetings between the researchers and operators. So that kind of works quite well. So if it's possible, I know it's not always possible, but I think it's a possibility. We can see whether it's possible to actually have a joint position, someone with a joint position between OIT and research. The first thing about more collaboration is finding problems that matter, and finding the pain points in production networks. You don't want to work on something that doesn't matter much to the operational folks. And this kind of actually finding this, it helps to have a joint position on this one too. So some examples we have on our campus is there were some cases where an operator had a hard time debugging the switch, which had occasional packet drops that switch, and it couldn't figure out why, did they have time for this, and it mentioned to us. Another example could be Wi-Fi performance, like Princeton is going this Wi-Fi first thing so that we can move wired connections to wireless. Is the performance good? Where is the bottleneck? Another example would be fingerprinting user OSs and devices for easier troubleshooting, because different OSs and devices have different issues. Can we categorize them somehow? IPv6 is coming on Princeton. We're trying to doing some work on this, but we don't have much experience. So can you help with that? Can we help with that? So these are real problems on campuses. And I tend to share this with researchers. So we actually had some successes here. We were able to run some programs so that we can do some queue delay monitoring to debug this issue on campus. For Wi-Fi, this is still in planning, but we're thinking of measuring RTT at different spots so that we find the bottleneck. Fingerprinting, we have a work in progress called P4OF, which fingerprints OS by inspecting traffic passively. So as traffic goes by, it can actually fingerprint. It uses the TCP SYN-ACK and stuff, and some quirks in there so that we can actually identify different OSs. Apparently, different OSs have different fingerprints on TCP option headers. And IPv6 on campus, we actually, this is more like an opportunity. We actually had a P4 app which was doing some IPv6 stuff. So we thought like, okay, can we test the IPv6 connectivity on campus, and we'll just leverage that and let you know how it goes. So now I'll share some success stories we had, starting with the passive monitoring with ConQuest. So OnTask kind of enabled us to do line rate anonymization so we can run ConQuest. And then we had active experiments with SPINE-DNS. And then we have some future plans about inter-campus testbeds. So I'll talk about that later. So briefly on ConQuest, it's a queue analysis P4 program. The problem the operator was having was a high packet discards on a particular port on a switch. It's actually our Science DMZ core router. But the link utilization was mostly less than 20%. And so we didn't know what was going on. Like, is it a bug in the switch? The switch is just bad? Is the OS problem? Or is the actual queue filling up? And when we asked the tech support of this particular switch vendor, they sent us PCAP captures. So it's like, oh, that's a lot of work. How do we even send this to you? Capture this? There's some PII in it? I don't want to do this. So it was a headache to actually send PCAP captures to him. So we said like, okay, we actually have an in-house research program which might be able to help. So the idea is you tap to the input and output of the switch, problematic switch, and feed that to a P4 program switch. And you will compare the two appearances of the same packet and calculate the queuing delay. And the good thing about here is it doesn't matter if the link is 100 gig or not. And if the delay is high, you will analyze and it reports what's happening on the switch. So these are some quick results we get. So it can actually measure the queuing delay on a switch. The left one is like there's one large steady flow, no drops. So okay, that's good. The right one is where you see a wide oscillation, and this is when we saw a lot of packet drops. So running this, we kind of confirmed, okay, it is a queuing delay problem. The queue or buffer is filling up. There is a problem here on that side. So this kind of gave us, okay, we should further investigate why this is happening. And we figured out, actually, we had about 20 object storage nodes behind this switch. And we had one persona node. And this one persona node was also talking to 6 other persona nodes on the internet too. There's also a problem about this being a 100 gig switch, but this hosts are a 10 gig switch. So there's a step down there. So some people may know, of course, that's going to have some problems. And we also figured out there was some back traffic going on between these object storages. There's a lot of traffic going on sometimes between them as well. And persona nodes were doing a lot of latency tests and throughput tests between them. So this is our guess here after doing this analysis. We think there's about 54 megabytes of total usable buffer. It's sometimes not that clear because which makes it kind of hard to figure it out. We think each port gets the same allocation. So clearly that's not enough of buffers per port. We can try to turn on dynamic buffer allocation, but the mix of different applications makes the operation hard. We also think Jim Warner, if he's on the call, he actually gave us some good tips about this too as well to figure out this analysis. So I think he read the paper on this and asked us questions and also clarified all of stuff for us. So thank you for him. So this was some good example of doing passive traffic monitoring using P4 and using real traffic. So more on ConQuest, we actually have a deployment on AT&T network too. They got really interested and they have some good results too. We're kind of working on it together. We have 2 papers on this. Danny has 2 papers on this. One was in ConQuest. The other one was in Stanford University, workshop on buffer sizing. So if you guys are interested, you can find out more about this work there. Okay, and let's go to the second application we have on hand, which is about DNS privacy. So DNS, how it works is you have an IP address, sends a DNS query, IP address, what's the address of census.com? I just made that up. The thing about this is, like, if someone is hearing on the public link side and you're happy to use a public IP address, which is not crazy in Princeton because if you have a lot of public IP addresses, and you can hear that and, oh, this guy's going to census.com. So this is a privacy issue. So the SPINE-DNS project is to actually anonymize this somehow per packet. So what's happening is we say the other side will have the Princeton IP, but the other side will also have a Princeton IP, but it's the IPv6. So if someone asked what DNS query, it'll get translated to IPv6 address, and it's actually doing a per packet hashing. That means if the same host asks the same question a moment later, it'll actually use a different address, not the same addresses. So it's kind of different with just natting. It's actually doing per packet hashing. So even if you're hearing that, you're kind of now unsure, and you're kind of impossible to actually pinpoint the original sender if this is the case, right? So we actually want to test this. Does it work in the real network or not? So this is not active anymore. This is not passive anymore. This is active traffic experiments. So we were able to convince the CS staff and some IT staffs on Princeton so that they actually give us a connection to the IPv6 internet so that we can talk to Google DNS via IPv6. It was good for them too because they can test their IPv6 connectivity, and they had a good training and practice in real world of enabling IPv6 on campus, not widespread, but still. So we actually made this work. A host was using some random private IP asking where's google.com, and then using P4 SPINE-DNS on the line, it'll translate and use an IPv6 address, which Princeton has. It goes to the internet, and we actually get a response from Google DNS coming back, Google.com is here, and it actually comes back to us. So this was a really cool experiment, which actually we had a successful running active traffic experiment through the Princeton network and through the internet, and to Google DNS and back. We can pick other DNS, public DNS as well. So this was really good. We have some future plans too about intercampus P4. Princeton is currently working with the Cornell so that we actually build the intercampus P4 fiber using NiserNet at 32 AOA at New York City. And we are hoping we can actually join, some other campuses can join too as well. And we can also think about connecting to Fabric. I think this is in plans too, so that we have a bigger intercampus P4 testbed as well. And you can think about end-to-end P4 experiments going on here. You can think about a lot of interesting stuff you can do. So to summarize this talk, it was about jumping the research chasm, being less disruptive, and you can do this by starting with passive traffic monitoring apps as a gateway drug. You can work on preserving user privacy. You have to do that. I gave some tips about IRP prep and more. Also using anonymization tools and line rate anonymization tools. More collaboration. Having a joint position kind of works, and you want to focus on problems that matter. So these are some important things that kind of worked for us. And we actually had some real deployment successes. One is P4 OnTest, which is actually used as the line rate traffic anonymization tool on campus. We have ConQuest, where we did some switch queue delay monitoring. P4 SPINE-DNS is DNS query extender anonymization. We actually had a successful test on this one as well. So we're actually asking the community, please join our effort. We want to jump this together, and that's why we are sharing our experience. Maybe you can find some holes or give us better advice as well. On our website, we have some example applications. We want more campus applications. Maybe different campuses have different use cases or applications in mind, and we want actually more from you if you can contribute. So this is like a call to arms talk, basically. And I want to thank everyone. This is our website. You can join our mailing list. I'm going to be more diligent on actually posting something on our mailing list. And thank you, and I'll take any questions.
All right. Well, thank you so much, June. Really, really fascinating stuff. First of all, I sort of secretly like the fact that you're using your entire campus for sociological experiments like this. I think that's a great use of your network traffic.
Yeah.
So I had a couple of questions come in, but I'll ask again. If people do have questions, please type them into the chat box, and I'll read them out. The first one is from Malathi at Virginia, and you may not be able to answer this, but I'll ask it anyway. Could you say a little bit more about how specifically P4 is being used in ConQuest or in SPINE-DNS? Basically, what new programming was needed for the packets in the data plane?
Okay. I'm wondering if the question is more like specifics of it.
Yeah, that's my guess.
Okay.
So if that's something you can answer, great. If not, maybe I'll just hook you up with Malathi. You can
sure.
offline.
Yeah, I mean, I guess of course more details can be found in that paper if you want implementation details. But basically, one has to write a P4 program using a P4 language and compile it and make it run on the P4 programmable data plane. But it's basically the nutshell. It's about detecting the same packet and coming in and going out, right? And it's in the P4 program, you're actually able to get the timestamp when it came in and when it's going out. So you're just basically subtracting that timestamp and storing it in the rest. So the programmable data plane has a stateful memory in it, so you can actually save those information bits in the switch itself. So the switch actually holds that information in it about the queuing delay, the difference of timestamps, and then later with the controller you can query those stateful memory to get the value. So that's like a high-level nutshell. I hope that kind of answers how it works. But of course, for more details, you can look at the papers here.
Okay. Yeah, and Malathi said yes, that was perfect.
Okay, cool. Thanks.
So I jotted down a couple here while we wait for others to come in. So my big question here is that, so you have this testbed on campus right now. How do you sort of advertise and drum up potential users for this? You had said that you're sort of the conduit into the CS community since you hold a foot in both worlds.
Yeah.
But is there sort of a general pitch that you make to researchers, or is there a way that you sort of try to do onboarding of the ideas to sort of vet them for if they're going to be possible, and also if they sort of conform to the human subjects rules and things like that?
So yeah, that's a good question. So basically, whenever I meet someone new in the computer science department, sometimes they already kind of heard about me, like, oh, if you want to run something really. So I think I've been here enough that people kind of like other students. I interacted enough with students that if they meet another student and that student says like, I want to run something on a real network, I can go to June. So I have a lot of students coming to me automatically, actually. But whenever I meet a new student or a new scholar or a new faculty, I mention it to them because I also go to a lot of meetings here, I mention it to them, I can do this for you. And they get interested in there. About human subject stuff, yeah, whenever, so they ask this, let's do this, then I have meetings with them, sit down with them, and then actually like explain what you have to do. Like you may need IB training. I have a pipeline of stuff the researcher has to do to have access to this. So yeah, we have a meeting, and then okay, you have to ready the IRB application, and then do the administrative data stuff, and then you follow these practices, and I'll work with you. So that's how it kind of works here right now. I think it'll be better to actually have a more structured thing. I'm thinking of doing something more structured too.
All right, thank you. And looks like a question was asked and answered via the chat already. So Julio had asked, is production traffic isolated from the experimental traffic? And Dr. Rexford stepped in and she said, for the passive monitoring applications, the production traffic is copied and directed through the P4 switches to perform analytics passively. And for the DNS spine application, we are testing first with the copy of the campus DNS traffic while having the real campus DNS queries handled the normal way. I don't know if there's anything you wanted to add to that or if that covers it.
That covers it, basically. Thank you, Jen, for answering that.
Okay. So that's all the questions that we've had so far. If anybody has any others, please type them in. I had one more. So at one point you had said, if you did try to capture all that traffic that was coming off of your taps and stuff like that, 1 minute of campus traffic was 45 gigs. So what sort of is the traffic, not traffic, what sort of is the data load on this now via the system that you've developed? I mean, are we still talking gigabytes per day, or have you been able to sort of pare that down a little bit?
You mean if it goes through ONTAS?
Yeah.
So ONTAS actually doesn't reduce the data rate or storage. I mean, it doesn't reduce the data rate. That's more accurate. But in storage wise, because you don't have to store the raw traffic first before anonymizing it, right? So you don't have two copies. So in the regular pipeline, you need the raw traffic first captured and then running offline anonymization so that you have a anonymized version of that. So you have two copies of different but kind of similar stuff, right? And then there's a processing delay of doing that. With ONTAS, what's happening is you just anonymize things on the P4 switch itself, so you don't have to save the raw packet anywhere else. And you have the anonymized live traffic coming out. And the thing here is, if you're still kind of capture that and save that, that's still a storage overhead. There could be still that. But the good thing is that you can also directly feed that to the researcher, saying okay, this is your problem now. Or the researcher might have a P4 switch, right? And he or she doesn't actually need a packet capture. He or she just needs a live traffic, but anonymized. So we can just give the live traffic and ask the researcher whatever she wants to do. So, but it doesn't reduce the bit rate.
All right, that makes sense. Thank you. We had two others come in. Jorge wants to know, do you implement all the regular protocols, IP forwarding, Ethernet, etc., in addition to your custom program? Do you have enough memory, or do you have to remove some regular features?
Oh yeah, that is a great question. So that depends on what kind of P4 program you have on the switch. Obviously, the programmable data plane has limited resources. If your P4 program kind of fits in there but doesn't have much space of other things, then you might not be able to do it. But if your P4 program is lean, then you may be able to do other protocols too. So the answer is actually it depends on the functions or array of functions you want to do in the programmable data plane. So I think for all the so for ConQuest, right, it doesn't need to forward anything. So it also depends on what your goal is. If your goal is to actually do regular IP forwarding and also do some cool stuff, you can do that. But you may be limited on what you can do because you have to do the regular forwarding as well. So that depends.
Okay. And last question, Malacy wants to know, in Ontus, are you stripping whole payloads beyond the TCP header or keeping any fields like in Zeeklog fields?
Zeeklog fields. So payload-wise, no, I don't strip out the payload if I don't have to. Yeah, that's the thing. So I don't strip out the payload.
Okay.
I can't, but there's the sometimes the application is like sometimes the researchers want to do snort or bro or some ideas, right? And in that sense, like payload is kind of important. But I kind of do that for them because they should not access the payload. So sometimes I have use cases where I have to keep the payload, but still anonymize the IP addresses and then run it and forward it to some places. But of course, if the payload is in there, I don't give it to the researchers directly.
Okay. So I think that's all the questions that we've had. I'll thank you again, June, for doing this. This has been great. For those that have also asked, the slides will be posted along with the video, and I'll get that uploaded probably a little bit later today. And to continue the P4 theme, we're actually going to have another related talk next week from Jorge at the University of South Carolina, and he's going to be talking a little bit about their work with P4. So if you like this one, hopefully you'll be able to attend next week as well. So the emails about that will go out later in the week. Hope everybody has a good weekend, and we'll talk to you soon.
Thank you. Thank you, Jason. Take care, everyone.